Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon and welcome. My name is Yuri Gurevich, and I'm here today to introduce and welcome Keith Devlin, who is visiting us. So I know Keith from old times when he used to work in set theory, where he proved himself beyond reasonable doubt. These days, here today he is on the occasion of his new book, and I'm sure the title will appear soon, so and the book is all there if you are interested or want to sign it. So Keith is the executive director of Stanford Center for the Study of Language and Information, a consulting professor in the Department of Mathematics. Do they need a consultant? A co-founder of Stanford Media X Research Network and of the University H-Star Institute. Sounds very important. I have no idea what it is. Probably the most important from many people know Keith from National Public Radio, where he is the math guy on NPR, and where he gives folks an illusion of understanding of things mathematical. He's also a World Economic Forum Fellow and a Fellow of the American Association for the Advancement of Science. So please join me in welcoming Keith Devlin.
Thank you. Okay, thank you. So before I sort of jump into the content of the talk, which is about this book, The Unfinished Game, I thought I'd say a little bit about how I came to write this book, because this is usually books that I've written a bunch of them, have been something that I wanted to learn about, wanted to know about. I'd enjoy the process of researching it, writing it, and would just actually enjoy producing a book. This was quite different. The publisher came to me, several years ago, 3 or 4 years ago. It was a guy I'd worked with, a guy called Bill Frucht at Basic Books, and I'd worked with him on the Math Gene, I'd worked with him on the Millennium Problems. And I'd had a good time with him. He's a good editor, and I was very happy to consider working with him again. And he said, Basic is bringing out a series called Basic Ideas. I'm not sure if that's... I need to check whether it finally did come out under that title. But the original idea was Basic Ideas. And it was documents, single documents, letters or notes that had been written that had changed the course of history. So single documents, small documents, a few hundred words, a few thousand words, which had managed to change history. The obvious examples have been things like the Magna Carta and the Declaration of Independence. Okay, so that was the idea. And he said, but we don't want them all to be just in the social, political realm, economic realm. We'd like some in the realms of science. And in particular, do I know of anything in mathematics that would classify as a single document that changed the course of history? And I said, well, the thing that jumped to my mind, I said, there is this letter that Pascal, one French mathematician, Pascal, wrote to another French mathematician, Pierre de Fermat, in the 17th century, which established modern probability theory. Now, I knew about that because the first time I ever took a course on probability theory at university back in England way, way long ago, on the first day of the lecture course, the professor comes in and says, probability theory can be traced back to a letter written from Pascal to Fermat in the 17th century. And so when I eventually got my PhD and started lecturing, the first time I found myself giving a course on probability, I began by saying, well, this goes back to this. Now, I never bothered to look at the letter or any of the history about it. I just took it on faith from my professor, and I suspect he did the same. Right? And a random poll I did of just a few friends brought up no one who'd even looked at this letter. Not even in the English translation, of which there are several available copies. You can just download PDF files of it now, or indeed the original French. So we've got this letter. I have an existence proof that there is this letter, and I want to use it, write a book about it. Haven't looked at it. So I go away and I tell Bill I'm going to do it, and I go away and I do some research. I sort of download all the files and get a few books out the library, look at some information, and within a very short space of time, realised that this is not just a story, this is an unbelievable story. And the odd thing is, no one had really bothered to tell this story before. I think because no one had bothered to look in any detail at the history. It was just a throwaway remark at the beginning of a course on probability theory. But it's actually one of the most amazing stories, not just in mathematics, but in human society. It's an incredible story. So within a short space of time, I'd gone from thinking, well, okay, this is what I'm going to be doing, to thinking, this is what I really want to do. This is a great story to write. In fact, I got so excited, and I'd got all this material, that I pretty well wrote the book in 3 weeks. Way the fastest time I've ever written a book. And I was writing sort of many hours a day, because I was just on a roll with this thing. And then I tell my agent, well, I finished it. And he says, for heaven's sake, don't tell the publisher that, because we haven't received the advance check yet. And if he thinks you've knocked it off, he's going to cut that advance by half. So he said, pretend it's going to take a bit longer. So I finished the book, I put it to one side. My agent looked at it and said, this looks pretty good. And I sat on it for 2 or 3 months. And every few weeks, Bill Frucht would call me up or send me an email saying, how's it coming, Keith? And I'd say, oh, we're making progress. We'll soon be there. We'll soon be there. And eventually finished the book. But it's an amazing story. And that's what I'm going to be talking about, the story itself. You might like to think that this is Sergey Brin's house, but it's not. This is any old house in foreclosure. And it's an all too sad sight at the moment of houses in foreclosure. And no doubt within the next 12 months there's going to be a parade of authors coming through Microsoft's campus trying to sell books on analysing what led to the mortgage debacle and the financial meltdown. Okay, those books, I'm sure, in the process have been written right now. But to my mind, an even more intriguing question about mortgages isn't how did things go so badly wrong, but how did we get to the position where we could give people mortgages in the first place? I mean, that's really weird when you think about it. We live in a society where we accept that ordinary people of ordinary means can buy and own a house. Really weird when you think about it. It's not that they borrow money from a friend or someone who knows them well to do it. They borrow money from someone who they almost certainly haven't seen, haven't met, and probably never will. They might not even see the agent they deal with. It might all be done over the internet. So people can borrow money to buy a house from someone that they have no prior contact with, based on answering a few questions. And that's a transaction that will typically take 25 or 30 years to pay back. In that space of time, who knows what's going to happen? You know, fires, floods, earthquakes, deaths, remarriages, people going to prison. All sorts of things can happen in a 30-year period, including the complete destruction of the piece of collateral for the loan, namely the house itself, or the depreciation of the value of the house so that you actually have a house worth less than the loan. So much can happen in 30 years. How can anyone be in a position to lend someone money under those circumstances? Long payback time, lots of risk involved. And moreover, lend that money in a competitive marketplace where the lender is competing with other lenders to sell you that loan. So it's a really weird that there's a very effective competitive industry in making loans to people in this sea of risk. Well, the answer, of course, is we can quantify the risk. No one knows what's going to happen in this district or to this house next week, next month, a year from now, let alone 20 years from now. But we can attach numbers to the way things might turn out with sufficient precision that we can actually fine-tune an interest rate to within 1/4 or 1/8%. And we just take that for granted, because we live in a world where risk management is just ubiquitous. People can do otherwise risky things. We can travel long distances. We can ship goods long distances. We can make expensive purchases. We can take automobiles that are worth $20,000, $30,000 onto freeways where there's lots of other vehicles with bad brakes and so forth. So we can do it all because we can attach numbers that quantify pretty precisely the future. But that's a very recent phenomenon. It's incredibly recent. In fact, what I'm going to show you is it's so recent that when it happened, the world literally changed. It was almost overnight. Certainly within a few years, within 5 years, 10 years, the world rapidly changed. And the key step was this letter that I'm going to talk about. And as far as I can tell, thinking about it, there's only been 3 times in history when mathematics has changed us. I mean, there are many times when mathematics has affected science and technology and changed the environment in which we live. We're used to that, right? The environment changes, going back to the Industrial Revolution and then the sort of physics, the scientific revolutions, the digital revolution, all of these changes tracing back to mathematics. So we're used to the fact that mathematics changes our environment. But there have been 3 times, and I can't think of any more that would really classify clearly, when mathematics, something happened in mathematics and people conceived of the world differently. You know, in a sort of metaphorical sense, it rewired the brain so that we think about the world, we encounter the world, we live our lives in a different way. And the first one is a pretty obvious one. It was numbers. Numbers are so ubiquitous that we can't imagine getting through an hour or 2 hours of the day without depending and using on numbers in one way or another. Even if we're the most math-averse person in the universe, numbers are everywhere, from the time when you wake up and when you have breakfast, when you catch the train, making phone calls, etc., dealing with money. So numbers are so basic that they are part of who and what we are. But they're quite recent. Based on a whole ton of anthropological evidence that's been gathered over the last 30, 40 years, we've been able to pin down when and where numbers came onto the scene. It was in Sumeria, in what was known as the Fertile Crescent region, largely now modern Syria and Iraq. And the process, it's a process that lasted 2,000 or 3,000 years, where numbers sort of crept in, and you can't pin an exact time because this is based on anthropological evidence, largely clay tablets and clay markers and little tokens. But the process is pretty well finished by 5000 BC. What led to the introduction of numbers? It was banking. Sumerian society had reached a stage of complexity that instead of just trading goods for goods, they felt it would be useful and efficient to have some people called bankers, or we'd call them bankers now, who kept track of someone's worth in terms of what we would now call numbers. That's how it cashed out. And so when you buy and sell things, it's in terms of the value, these numerical values, and you don't have to sort of just do trade for trade. So we get the beginnings of a modern society, at least in the sense of a banking system, carrying with it the one thing that bankers need, namely numbers and some basic arithmetic, around 5000 BC. So that's pretty darn recent. And I think it's fairly self-evident that we are different from people without numbers. We can't imagine what life would be without numbers. We can imagine life without lots of things. Most of us can actually remember life without most of the things we use today. But numbers are just part and parcel of who and what we are. Our world understanding and our world way of living is based on numbers. So there's one time when something in mathematics just changed the way ordinary people, not just technical people or specialist people, live their lives. The second one would be the scientific revolution. The idea that you can take those numbers and hang them on the world in order to understand the world. Now you have to sort of do some postulation, you have to introduce, invent, discover, call it what you like, things like force and mass, velocity, acceleration, work, all of these terms that temperature, that we typically use when discussing the world. And then you could have put numbers on them, and as Galileo said, and various other contemporaries said, the best way to understand the world, or maybe the only way to understand the world in a useful way that will lead to science and then technology, is to put these numbers on the world, attach numbers to things in the world, to various features of the world, and study the numerical patterns between us, and thereby gain a kind of understanding of the world. And it wasn't just scientists and technologists and engineers that sort of took that to heart. Everyone does now. We talk about temperatures, we talk about force and work and so forth. It's part of how we understand the world. We understand the world, even if we're not a math type person, people understand the world through a basic numerosity of numbers attached to the world. And we make many of our decisions in terms of those numbers attached to the world. Temperature is one, pressure is one, various sort of numbers that are attached to the world.
Go to the Hellenistic period.
The what?
Shouldn't you start from the Hellenistic period, this revolution?
I mean, you can trace some of these things back in different parts of the world. I'm taking a simplistic cut through, okay, and attaching some particular moment. Okay. And then there was a third one. And this one, I think, is a pretty clean one. And it was certainly very rapid. The others, as Yuri mentioned, there's sort of other traditions and time scales you can look at. Okay, I mean, the elements of modern science, you can certainly find a lot of that in Archimedes' writings. So you can trace a lot of these things back. But this one is really dramatic. And this is, as I said, this is the story that I didn't know was waiting to be told until I looked into it. The idea of predicting the future with numbers. That means hanging numbers not on things in the world we live in, but hanging numbers on tomorrow and next week. And as I'll show, and as became clear to me when I read the various articles and documents relating to this particular letter, that was something that was just thought not to be possible. And this is one of the moments not only when we pin it down to a particular, I mean there's obviously other stuff going on, but there's a particular letter, the one that I was aware of and everybody else that's taken a course on probability knows exists. The letter written on Monday, August 24th, 1654, it's a Monday, right? And it was a letter about a thing called the unfinished game. So the title of the talk is The Unfinished Game, and that's one of the names given to this problem. Another name is the problem of the points, and there are various other names. But those are the most common names, the problem of the points, the unfinished game. And it's as the name unfinished game might suggest. Two gamblers are playing a game. It doesn't matter what it is. In terms of the problem as Pascal and Fermat looked at it, it was rolling dice. And they're rolling 5 dice. I mean, they're rolling 2 dice 5 times. And it's a best of 5 game. Okay? 2 people rolling 2 dice, best of 5. They play 3 rounds, and one player then is ahead 2-1, say. And at that point, they have to abandon the game, but there's money in the pot. The question is, how do you divide the pot fairly based on who's in what relative position in the game? You want it to be a fair division based on how far the game has progressed, knowing that the game can't be completed. That's the problem. It's really easy to solve. In fact, you can explain the solution to high school students or younger if you have in a couple of hours to give them the background. Not a difficult solution. And yet, when you read this correspondence between Pascal and Fermat, Fermat, I would say, is one of the best 10 mathematicians ever. Pascal is certainly a great mathematician, did a lot of good stuff. Pascal, in particular, is struggling to understand the argument that Fermat comes up with. I'll give you a little bit more of the history in a minute. But I want to focus in on the fact that you've got a couple of great mathematicians struggling, and this letter is part of a correspondence that takes place over several months in the summer of 1654. 2 great mathematicians struggling to solve what we would now regard as a simple counting argument. We've got to ask ourselves, why was it so difficult for those guys to do it? They knew how to calculate the odds of rolling dice. They knew that if you roll 2 dice, the probability of getting a double 6 is 1/36 and so forth. That kind of stuff had been known for at least 100 years, and the basic ideas of counting patterns of dice rolls goes back at least to the 10th century. So people were used to calculating odds in the gaming rooms and using those odds in order to improve their performance in games. And yet they seemed incapable of taking the same counting idea and applying it to the future. Well, I'll come back to why I think it was particularly problematic for them. But first of all, let's just look at how the letter begins in the English translation. Monsieur, this is Pascal to Fermat. The background is a little bit more of the background. Pascal has written to Fermat because he can't solve the problem and he wants Fermat's help. He hadn't met Fermat. In fact, the two were never to meet. They just corresponded for a brief period in the summer of 1654, and then a few more letters later on, leading up to Pascal's death at the age of 49 due to cancer. So they've had some correspondence. By the way, there are 7 letters still in existence. The original letter from Pascal to Fermat is no longer existent. At least we don't have a copy of it. We have the first one we have in this correspondence is a reply from Fermat to Pascal. And then we have 3 of Pascal's letters and 4 of Fermat's letters altogether. That's all that we have access to that are known to exist. But the complete letter in the middle of this, or just over halfway through the correspondence, we have that letter. And this is the definitive one, because the correspondence has gone on far enough that each person, Pascal and Fermat, has explained his best attempt at a solution, and Pascal summarizes them and analyzes them. So this is the letter that nails it. This is where we see probability theory coming out. Okay. I was not able to tell you my entire thoughts regarding the problem of the points, that's the word he's using for it, by the last post. And at the same time, I have a certain reluctance at doing it, for fear lest this admirable harmony which obtains between us, and which is so dear to me, should begin to flag. You've got to remember, these are the equivalent of academics, professors. Have you ever known two professors so polite to each other when they disagree about how to solve a problem? You know, the standard phrases are, you stupid jerk, why don't you see how to do it? That's what we learn at graduate school. Okay, but this is unbelievable. That's kind of nice. In fact, in the book, I repeat the whole letter. When I was starting the project, I didn't know I was going to do that. But I was so taken by the wonderful flow of this thing that I just repeat, I unfold the letter as the book goes through and then repeat the whole letter at the end for reference. It's wonderful language. This wonderful... For I am afraid that we may have different opinions in this subject. One of the things I hope comes out of this book is that teachers will show it to students of mathematics. Because anyone who's been in the business of teaching mathematics for several years knows that a lot of students have come to think, or do come to think, I just can't do this stuff. I just don't know how to solve it. I don't know how to get these ideas. And they usually form that conclusion because they've tried to work on a problem maybe for half an hour, or maybe for an hour, or maybe for an evening. And they get this sense that if they can't solve it overnight, they don't have what it takes. And they have this belief that mathematics springs forth from certain people's minds and looks like the stuff that appears in textbooks. Of course, it ain't like that at all. Textbooks have been refined and polished over thousands of years. The kind of stuff we teach is usually old stuff. And it's run through the mill of many, many people, and it looks really slick and polished, and it's lost all of its historical mess. Anyone who does mathematics knows it's very different from that. It's a messy, guessy, make lots of mistakes kind of process. But that almost never gets published. That gets buried away. In fact, people don't publish that kind of thing. Some of it occasionally comes to life when they look through someone's papers after they've died and they produce some sort of collection of papers, but nobody ever reads those. Here we've got a great story of obvious relevance to the world where you can actually dive in and see what it's like to do mathematics. And one of the subtitles, a little subtitle on the book, which is the one I insisted that we put in and the publisher didn't want to do because it's a second subtitle and they don't like two levels of suffixes, it's called A Tale of How Mathematics is Really Done. Because here we see mathematics really done, and we see in particular Pascal, this pretty smart mathematician, making stupid mistakes and just getting it wrong and simply not seeing it. And so it becomes clear that even the great mathematicians achieve greatness. Well, they certainly do have more ability than the rest of us, but the other thing that they have is they keep going until they get it out. And they keep playing with it, and it's not somehow an instant brilliant idea. It's a brilliant idea that may have come after a long struggle. And that's laid bare in this thing. So I'm hoping that when teachers sort of encounter this from students, they say, look, take a look at this thing and see what it's like when a couple of great mathematicians are attacking a new problem. And the nice thing about this one is the student can understand the final solution and then can maybe say, wow, this isn't difficult. How come those two great guys took so long to find it? Okay, I wish to lay, this is Pascal still, I wish to lay my whole reasoning before you and to have you do me the favour to set me straight if I'm in error or to endorse me if I'm correct. He's got his own argument. It's not a very good one. In fact, the hardest thing in the book is to follow Pascal's argument. It's a sort of a hideous recursion argument that just gets hopelessly messed. So it's not a nice argument. You can make it work, but it's messy and intricate. But he's not even sure if it's right. He's got it, and he's just unhappy with it, and he showed it to some of his friends. So he wants Fermat. By this stage in the correspondence, if indeed not at the beginning, Pascal has recognised that Fermat is by far the better mathematician. And it's conceivable that Fermat actually solved this problem within a couple of hours of seeing it. I mean, we don't know. He may well have done, but he certainly had nailed it by the time he got to this letter in the correspondence. I ask you this in all faith and sincerity, for I am not certain even that you will be on my side. So we've got two potential proofs being discussed. Okay. The Fermat proof is the one that we now take as the standard proof. It's so basic that a few years ago, when I worked on a PBS service called Life by the Numbers, we didn't have any hesitations, we being me and the producers, didn't have any hesitations, including a clip about the solution. In fact, giving the entire solution. So rather than just give you the solution in my voice, I'll let Danny Glover speak my words from that movie.
The problem that piqued Pascal and Fermat's interest revolved around a game of dice that comes to an untimely end.
Suppose two people are playing a game. They're gambling with each other, and halfway through the game, they have to abandon it. One person is ahead of the other person at that stage. Question, how do they divide the pot so that it's fair to both? Now, if you think about it, that means you have to look into the future, the potential future that would have happened had they been able to complete the game.
In a series of letters, Pascal and Fermat imagined a game of dice to be played in 5 rounds. The first person to win 3 rounds wins the game. In their scenario, they imagined that Fermat was ahead 2 rounds to 1. Fermat just needs 1 more round to win. Next, the mathematicians looked at all the possible outcomes. For example, if Fermat won rounds 4 and 5, he would win the game because he would have won at least 3 of 5 rounds. If Fermat won round 4 and lost round 5, then he'd win again, because again, he won 3 of 5 rounds. If Fermat lost round 4 and won round 5, he'd still win. In fact, the only way for Fermat to lose would be if he lost both of the last 2 rounds. Given these possible outcomes, Fermat and Pascal correctly reasoned the odds were 3 to 1 in favor of Fermat. Therefore, Fermat should get 3/4 of the pot and Pascal 1/4. The mathematicians calculated how a slight edge would result in one player winning more often than not.
Okay, so it's just a standard, simple counting. You've got a space of possibilities, and you count the possibilities A and the possibilities B, and that gives you your odds. Well, as I mentioned earlier, going back to attempts at the beginning in the 10th century, people had developed the ability to look for repeating patterns in rolling dice and calculate the odds of various things happening. Are you more likely to get a 10 than a 9 when you roll 2 dice, that kind of thing. All that had been done, and people knew how to do it. There'd even been books written on that kind of material, not really for mathematical interest, but for gamblers to be able to improve their performance. So people knew that. Why couldn't they do essentially the same counting argument here? Well, here's, I think, I can only find one explanation from looking at all of the stuff that was written, and it's this. What's going on here is they're trying to hang numbers on something in the future. You don't have to do that in order to work out the probabilities of how things will happen when you roll dice. You roll dice many times and you see how they happen and you reason about them, and those are numbers in the present. You can then predict the future simply by the reasoning that says, well, dice are inanimate things. What they did last week and they do today, they'll do the same things tomorrow. If we've observed that you get a double 6 roughly 1 out of 36 times when you roll 2 dice, that's the pattern we've observed by hanging numbers into today's world, and we can confidently assume that tomorrow when we roll the next time we roll the dice, it's the same. So the numbers have been hung on today, which we've got used to doing since Galileo and various other people. We know how to do that. Here, it's a game that hasn't been played out, and you've actually got to think of how the game might be played out in the future. You definitely need to hang the numbers into the future. And that, I think, and when you read the way Pascal's talking about it, that, I think, is the problem. What's interesting is today, it's not a problem. Not only is it not a problem, but we will see it essentially as the same argument. You're just hanging numbers, you're putting numbers on a tree of possibilities, and you're counting. The fact that we see that as such an obvious thing to do, I think, reflects the enormity of the cognitive shift that took place when this was done. The logjam was the belief that you could not apply mathematics to the future, a belief which goes back certainly to the ancient Greeks. Aristotle wrote about that amongst others. You can't apply mathematics to the future. It's unpredictable. And indeed, if you've got something that you don't know that's happened, if you have to assign numbers, it's 0.5 or 50%. Tomorrow is uncertain, so the natural way, the only way you could rationally assign numbers is 50%. And some people who looked at this problem actually said that. Okay, so there again is the letter. That's what they were talking about. That solution we saw was Fermat's. Pascal gives it in his book, in his letter, and looks at it and reasons about it and tries to do what mathematicians do and say, well, imagine that it wasn't 2 dice, it was 3 dice or something. He sort of looks at generalizations and tries to punch holes into it, and also tries to advance his own argument, which, as I say, can be made to work, but it's rather complicated. Let's just look at so that's the story. Let's just look at what happens pre and post that letter being written, because things were very, very dramatic. There's a huge shift. The problem itself goes back, we don't know how far it goes back, but it was first appears in print as far as we know. The first known appearance was in 1494 in a book written by Luca Pacioli, who was a contemporary of Leonardo da Vinci. But we know for sure it wasn't his. He was just reporting on it. So we've got an imprint in 1494. He tried to solve it, didn't find a solution. Cardano comes along, a very interesting guy. He almost steals the show in terms of the book story because he had such an interesting life. He was a medic and a philosopher and a mathematician and a hell of a gambler. Well, hell of a gambler suggests he won a lot of money. No, he was just a compulsive gambler. He tried to do it in 1539 and failed. He by the way, he wrote a book for gamblers, a book called, translates roughly as the Book of Games of Chance. And in that book, he did pretty well nail the modern calculus of probabilities, probability of if you've got 2 independent events, you multiply the probabilities, all that kind of stuff. So he got the basic calculus right, and he was able to calculate the various odds in rolling 2 dice and that kind of thing. So by 1539, we've got books that tell you how to calculate the odds in the gaming rooms. But he wasn't able to apply those techniques or his techniques to this particular problem. Tartaglia, whose name comes up in the history of algebra amongst other places, he tried and then said, you can't use mathematics to this kind of a problem. It's about the future. You don't know how the game would have finished, therefore you can't apply mathematics. So did this other guy, another mathematician. He came up with a solution, sort of said, well, we'll split the pot in part on how many games they've already won, but then there's the rest of the game, and that's in the future, so we'll have to split it 50-50 based on that, and we'll combine the original games won with 50-50 for the rest. And then sort of basically saying you actually can't apply mathematics to the future. So you can apply mathematics to the rounds they've played, but you can't apply it to the future. Even the same mathematics won't apply. So you've got these people with good credentials in mathematics, and who knows how many people less credentialed didn't make any progress. Then along comes a minor French nobleman, the Chevalier de Marais, not a mathematician but a gambler, and in 1654 he asks Pascal about it. A friend of Pascal. Pascal's not a gambler. Actually, Pascal at various stages in his life was a gambler. He sort of became a gambler, then he was ultra-religious, then he was a gambler, then he was ultra-religious, and he kept coming in and out of that. Pascal tried it, as I mentioned, came up with an idea, but a rather complicated proof with sort of regression formula and sort of recursive process. But he's unhappy about it, doesn't know it's going to work, and so writes to Fermat. The letter gets written, and then things happen really fast. Within 3 years, you've got a pamphlet, a 16-page pamphlet been written by Christian Huygens, which is essentially a modern textbook in probability theory. It's there. Pretty well everything except Bayes' theorem, which comes later, is there. You've got it. It's nailed it. Doesn't use modern terminology. That's going to come a little bit later. But all the basic ideas were there, including the notion of expectation, which he introduced. Then a serendipitous event happened in England when John Graunt, quite independently of these, not a mathematician at all, a haberdasher in London, he comes along and for whatever reason, and no one knows quite why he did this, but he decided to analyse the mortality tables from deaths in London. That was at the time the plague kept coming in and out, so there was a lot of interest in mortality tables. And so he analyses them and essentially develops the beginnings of what we'd now call inferential statistics, because he has to manipulate this data to make up for missing data or obviously incorrect data. So he has to process the data to make it look reliable, thereby establishing the basics you'll need in order to take probability theory out of the gaming rooms, where you can argue by the symmetry of the dice and so forth how the things would come out, and apply those techniques in the real world where you have to have some initial distributions to apply your probabilities to. Huygens then gets back into it and says, wow, yeah, we can start to apply this to the world. So he uses the more mathematical probability theory he's worked on to do a much better analysis of the data that Graunt had got. Then this young Dutchman, who actually became the Prime Minister of Holland before he was killed, assassinated at a very young age, he was fighting some war or other, and there were wars all over the place in Europe then. And in order to fight the war, he wanted to raise money, and he thought he would do it by selling annuities, and he wanted accurate mortality tables to be able to competitively sell annuities. And the result of his analysis, which was much more sophisticated than Graunt's, was actually that Graunt had done a pretty darn good job with the tools at his disposal. Halley of Halley's Comet comes along and does the same thing with some more accurate data. But look, we're still 1654, we're still within half a century, we're still within a lifespan, a professional career, in fact. And we've got all of this coming down the pike. Then the Bernoullis get in on the act, the famous Bernoulli family, of which at least 4 or 5 were very established mathematicians. In 1709, Nicholas Bernoulli applies it to legal and court matters, takes probability theory into the legal system where it has remained ever since, and where it's currently very hot property. There are various cases stacked up in the appeals courts around the land, capital cases, that depend upon the fact that the statisticians and the probability theorists can't agree on the best way to calculate probabilities for DNA identification accuracy. And there's a lot of dispute about how you should best calculate the probability that a DNA identification is not just an accidental match of 2 profiles, but is in fact a result of the fact that the sample is the sample of the guilty party. So we got this applied in the courts. One of the early problems was, if someone's disappeared, how many years do you have to wait before the courts can declare that person dead and you can divide the estate? And that depended on accurate mortality tables that the courts were prepared to accept. Another Bernoulli comes along and actually introduces the word probability in a book which wasn't about gambling per se, but was really about predicting the future. Now you've got the recognition, quite explicit, that this is about conjectures about the future, about coming to conclusions about the future. You don't know what tomorrow will bring, but you can put numbers on how it might turn out. Among other things, he proves the law of large numbers, the thing that says essentially if you get a big enough group, then it's representative of the whole. Easy to say in everyday terms, pretty tricky to even state properly, let alone to prove, but that's another issue. De Moivre comes along, still within 100 years, still less than a century later, with the bell curve, the last nail in the coffin for applying all of these techniques to the real world, looking at real world data. And then the one thing that was waiting to come on board, which was different, was the alternative conception of doing probability theory that Bayes brought in 1764. But I put that in not because it's so much part of the original story, but that's the one missing piece of modern probability theory. And when you've got that, you've got it all. And you've got it, 1764, just over 100 years after that letter, you've got everything. You've got most of it long before that. You've got most of it within a couple of years. So you've got this rapid change. And on the heels of this, you've got people making money out of it. Insurance industries coming down, people that do statistical consulting and so on. You've got all of that stuff coming very quickly on the heels of this. It was very, very dramatic. And this is why I was blown away when I read this story. You've got this belief that it's impossible. It wasn't just that they didn't know how to do the calculation. I mean, from our perspective, they did know how to do it. They just didn't apply what they knew. But from their perspective, not only did they not know how to do a calculation about the future, the firm belief was it was impossible. And I think that's why they didn't know how to do it, because there were, nothing hinders advances more than thinking you try to do the impossible. So they simply thought mathematically you couldn't apply numbers to the future. And then suddenly this letter gets written. And then it's interesting it happened so quickly, because, they didn't post it on YouTube, right? It had to get out, and it was a handwritten letter. So on the other hand, you've got two groups of people interested in it. You've got the academics, for whom this is clearly fascinating. And you've got gamblers, including all of the influential people in Europe, who want to know anything about using mathematics in gambling. So you've got two networks that can spread it quickly. So we can sort of understand the mechanics, but it's still dramatically quick how things come tumbling. And the modern world, in terms of risk management, just comes within a few decades, and within 100 years, it's all there. Everything we now take for granted about insuring, offsetting risks, the mechanics for doing that comes. And it comes on the heels of thinking it was a total impossibility up to the writing of this letter. This is why I was just blown away by this. It's just an incredible story. Interestingly enough, that clip we made there's nothing worse than seeing a video clip of yourself 10 years earlier. It makes you realise how old you get in 10 years. Which, looking in the mirror each day when you shave, gives you this feeling that everybody else is getting old and you're not. And then you see a video and you think, holy, whatever. So, very, very rapid change coming on the heels of this one letter. Okay, and everything we take for granted in the modern world about risk management coming from it. So as I say, it's an incredible story, a most amazing story. As I say, when I worked on that video, it was interesting that we sort of said the story. I haven't said anything in the book in a sense that I've said a lot of things in the book that I didn't say in that clip. I knew the story. I sort of even looked at it a little bit when we were working on a TV series. What hadn't come across to me until I looked at all of the other stuff that was going on was just how huge it was and how quick it was. It was a revolution. And it's a revolution that affects everyone, because everything about, and the subtitle of the book is something like Makes the World, and the 17th century letter that made the world modern. Because that was where the modern world come. The modern world that we live in is a world built on the one hand on science and technology, tracing back to the scientific revolution and so forth. And the other one is risk management, predicting the future. We do almost nothing without having some numerical sense of the future. And if it's only looking at the weather forecast, the future comes today with numbers. And if we hire consultants or we pay someone to make decisions for us, it's all based on numbers. And that letter was it. I mean, this really was a document that changed the course of history. Here's how the letter ends, just for the way of completing the talk. These, monsieur, are my reflections on this topic on which I have no advantage over you. This is still Pascal, except that of having meditated on it longer. But this is of little advantage to me from your point of view, since your first glance is more penetrating than are my prolonged endeavours. This is kind of interesting, because he's reached that stage that he can recognise Fermat is almost certainly right, because you get that sense. But he still doesn't believe the solution. He's still unhappy about it, and some of his friends don't think it works either. So it's a sort of, yeah, okay, you're much smarter than me, you're almost certainly right, but I can't get my mind around it, and I sort of don't believe it in some sense. And I'm sure many of us have been in that position when you're working with a really smart person, and you think, you're probably right, but I just don't get what you're trying to say. I beg you to inform me how you would proceed in your research on this problem. Well, in fact, Fermat had already stopped looking at the problem. If you read the rest of the correspondence, having solved the basic problem, Fermat's mind has moved on. He's lost interest. He cursorily answers, or fairly briefly answers some of Pascal's questions, corrects some of his mistakes, but he's moved on. He was actually looking at what we now call the Fermat numbers. He was actually in the process of making one of the few errors he ever made, namely the claim that the Fermat's numbers are all prime. Okay, so I begin for how you proceed in your research. I shall receive your reply with respect and joy, even if your opinion should be contrary to mine. So he knows that there's still a disagreement and he can't really resolve it. A few more letters get exchanged, but by then it's all been nailed. It's never clear if Pascal ever does really understand the proof, or whether he buys it in his heart of hearts. But he certainly is blown away and bowled over by the force of the logic of Fermat's argument. Okay, that's the end of the PowerPoint part, and I'm happy to take questions until we have to get out of here. Okay. And how do we do questions? Do I need to repeat the questions, or people just... Okay.
I have a question about, so the fellow I mentioned earlier, who, I wrote him down, Cardano, who wrote the gambling book earlier. So what I didn't understand is that you're saying that he did write a book that was useful and probabilistically motivated, that was helpful to gamblers, but how could that not have been a predictive book?
Yeah, so the question is, Cardano writes this book, so essentially would translate something like the Book of Games of Chance. It's in Italian. Okay, and it is about calculating the odds and using them. Cardano, he's many things. He was a professor of mathematics at one stage and a professor of medicine. He did a whole bunch of things. But he was predominantly a very keen gambler. And his life is largely a mess because of losing money in the gaming tables. And the question is, he's worked this out. He's written this how-to book for gamblers about how to cast your bets for the future. So isn't that predicting the future? And if they could do that, how come they couldn't do essentially the same, actually, and a somewhat easier calculation? That's a very simple calculation that we showed in the video. How come they couldn't apply that to that problem? And I think it does come down to this question. I thought about this a lot. And the only explanation I can come up with, and the one that I give in the book, is this. First of all, we have to factor out how we see the world. We live in a world where we know that you can hang numbers into the future, and you can reason about the future numerically. We do it all the time, and if the arithmetic's too complicated, we hire somebody else. We hire some forecasters, some consultants to do it for us. So we know you can hang numbers into the future. Let's go back to the ancient Greeks, and for a couple of thousand years after that, up into the middle of the 17th century, when people's belief was, if they had a belief at all, if asked, can you hang numbers onto the future, they would say no. So we have to then understand what Cardano thought he was doing and what people were doing when they were betting in the gaming tables. And here's what I think that they were doing. They were saying, you roll dice and you can actually see regular patterns. By the way, Galileo looked at this empirically. He actually rolled a lot of dice and counted the probabilities of the number of times things came up. So he did an empirical study, in particular of rolling 3 dice and looking at the numerical patterns, because that was his game. His game was look for numerical patterns in the world we live in. So you roll lots of dice and you count the outcomes, and then you reason about them and say, well, the dice is symmetrical, and so if they've got 6 faces, so roughly a sixth of the time. So you can reason, you can do it empirically, or you can reason in sort of quasi-empirical way as to what's going on. So you recognize that the world is such that whenever you roll dice, in the world we live in, let me stretch that, in the world we live in, when you roll dice, you get these repeatable patterns. Unless something is going to change the nature of how dice will come out, what you've observed and thought about in today's world is what's going to happen tomorrow. So my interpretation of why there's this sort of difference in view of these two problems is that in the case of calculating the odds of dice, what they're saying is, we can hang numbers on the rolls of dice in today's world, and based on that, we can make the inference that tomorrow's world will be the same. So that's the numbers have been calculated in today's world, which we know we can do. To solve the problem of the unfinished game, you have to think of possible futures, which is something we talk about. That phrase itself, possible futures, that's fine to us. In the 17th century, that must have seemed like some new age magical term. Possible futures? What on earth? That kind of thing. I mean, looking into the future as it might or might not have come out and hanging numbers onto the future, I think the stumbling block was that to do that argument, you're reasoning, you're putting numbers onto possible futures. You're not putting the numbers onto events in the world as it is. You're looking at numbers attached to events in a world, and you're attaching those numbers to things that might not happen. Because in fact, you've got all those possible ways the game might come out. If the game had been played out, it would have only come out one of those ways. And so you're attaching numbers to things that never actually happen. Not only are they in the future, but they would never transpire. So I think it would that I think is the cause of the problem. How does it cash out? It actually cashes out in practical terms. And when you read Pascal's trouble with Fermat's argument, you realize what's really behind it. Because he says, look, you're counting as if they've played all 5 games. But in practice, once one player has won 3, they've won the best out of 5, and they'll stop playing and they'll start another game. So Pascal is saying, look, Fermat, you're modelling the world wrongly. You're modelling the world as if these 2 people were stupid, and they would play their 5 games out, even though one person has won 3 and won the best out of 5. So you're even modelling the world wrongly, and therefore your answer is going to be wrong. So it was this belief, or this lack of confidence that you could apply numbers effectively in the future. Because there are 2 ways you can do it. You can do the calculation based on the fact that they'll play until one person has won 3. It's a little bit more complicated because you have to look at the different probabilities of how when the game would end. But you'll get the right answer. You'll get the 3 out of 4 answer if you do it that way. Or you do it the way Fermat did, which says, imagine the players are forced to finish all 5 games because those are the ways the world will come out. And I think that's Fermat's brilliance. He looks and says, what we do is we look at all the ways the world could have come out, and then we do our counting. The counting is the same as just any kind of probability counting. The only thing that's changed is the probability space, and it's in the future. I don't have another explanation, but I get your point.
But it just seems that a mid-game bet would be exactly the same scenario, right? Like if you're in the middle of the game and you need to make a bet, then you're effectively in the unfinished.
And I think we find that obvious because we were born in the 21st centuries, and I think if we'd been born in the beginning of the 17th century, I think we'd have said, oh, wow, yeah, because that's what all the smart people did. This is why I think it's a hell of a story, because it's trivial to us. It's the way we think about things. Now, we're a techie crowd, and we're used to these kind of things, but people sort of do reason about the future all the time. Yeah.
I think, actually, my question probably has exactly the same answer.
Oh, okay,
it seems like this goes back way further, because millennia earlier, people were banking, using numbers for banking. And there did exist a concept of interest.
Yeah.
So there was a notion of, if you pay me back tomorrow, this is how much you will owe. If you pay me back this next month, this is how much you owe. So there's something predictive. But is it just the idea of multiple possible worlds that was beyond the scope of reasoning at that time?
Yeah, I think it was being scientific about it. I mean, being scientific essentially means, in our terms, means you're hanging numbers onto events. And I think, yes, there was all of this reasoning going on, and some of it was numeric, but it was all, where were the numbers being hung? The numbers were being hung on the future. Yeah, you're inferring the future based on the past. That's what humans always, the best strategy is assume tomorrow is more or less like today. And so you infer based upon, we wouldn't have, well, we can go into the mortgage crisis, but I mean, if we'd carried on using the rules that have been working fine for decades, we wouldn't be in the present mess. It was people gaming the system around the edges. But yeah, I think it's where those numbers are getting hung, and it's this idea of possible futures and sort of doing a scientific, mathematical calculation in the future. That's the only distinction I can see. But the challenge we have is we're brought up in a world where these things look like the same problem. And they weren't, and we're forced with, and this was part of the book. The book, by the way, is in a series which is meant to provide an interpretation of why that letter was important. So this was part of the genre that they were looking for. That the editor said, come to a conclusion. Don't write the book and say, maybe this, maybe that. I mean, in fact, I only came to one conclusion anyway, but it is meant to say, here's my slant on how this was and why it was important. And the only distinction I can make is that if I were able to, and I'm not, to put myself in the mindset of those guys, it would have seemed like a very, very different problem. And the fact that it's gone from being an impossibly different problem to being, what's the big deal? To my mind, that measures, boy, something really big happened when that was done. It was a huge cognitive shift, yeah.
So I'm wondering, when they tried to prove this, did they actually look at each numbers of what numbers being rolled out at each round? Because it seems like the general assumption here is, if you look at the round level, the probability of winning for each person is the same. That's the general assumption. That's why you get the probability right. Otherwise, you won't get it right.
I mean, the only answer I've got is I don't know what was going on when they were working on that thing. I mean, all we've got is the letters that were written about them, and it's really, I've said all I can conclude on the basis of what I've seen, and I don't know if there's any other evidence as to what was going on.
There are several books talking about, like, one person was saying there are 2-1 in the previous 3 games, then 50-50 on the other games. When they make arguments, are they based on the numbers being rolled out, or based on the assumption that in each round there were 4 points?
Pretty well anything that you could think of was tried. And there were certainly people who said you base it on the games that have been played, which is actually the wrong thing. You really have to base it on the unfinished. That's why it's the problem of the points. Actually is a good way of calling it, because you sort of assign points, hypothetical points, based on the games that haven't been played. But until Fermat comes along, no one successfully thinks about how you assign the numbers based on the games that are still to be played. They can make a good job of they know the games to be played, they know how to count that. But the guys that did this sort of hybrid, in terms of the future games, they ended up saying, those games are in the future, those rounds are in the future, so it's 50-50. I mean, the assumption seems to be that, or was in those cases, if it's in the future, the only numbers you can assign is 0.5. And that's the best they could do, which basically means we can't think of how to apply a number at all.
So this is a private correspondence.
Yes.
How did this correspondence influence?
The conjecture, and I think you can sort of see how the things would have happened. You've got two groups of people interested. You've got the mathematicians that are interested, and Fermat, of course, writes about stuff to everybody. But I think that I would say that most likely what got it out quickly was the gambling community, because this was of great interest to them. It gets back to Chevalier de Méret. These guys are gambling all together. So you've got this group of wealthy people travelling around, influential people, and these are compulsive gamblers. Anything related to how you might, and it's not clear that this really helps you win in the gaming tables, but anything about calculating odds is going to get through very, very quickly. So you've got this big social network of gamblers, and that would be my read as to how this got out so quickly, and it did get out very quickly. The exact path that gets it to Christian Huygens, I don't know. I don't know whether Huygens was a gambler or not, but within 3 years, he's taken these ideas and polished them all off very nicely. Yeah.
This kind of like, we're looking at this from the perspective today. Do you think that there are 2 questions? One is, do you think that there are fundamental things such as probability theory that we are missing out on? And the other one is related to more to your language side of things, to say that we should start questioning all our base assumptions. Things like science should be tied to maths is a nice way of understanding science, or because maths may be a self-limiting thing, which is not making us think of like redoing. I guess set theory probably makes sense, and then rebuilding a whole new language on top of that is more relevant to science rather than to like practical engineering applications that maths tends to. So there seems to be a positive bias in terms of how maths has evolved, where things that are successful, like probability theory, are well entrenched, versus like maybe we are self-limiting ourselves to be rediscovering. Do you think there are any fundamental things left to be discovered, such as that? We're just fooling ourselves that we know.
I just, let me answer them in reverse order, because as I've got older and more reflective, as one does when one gets older, I've actually got very interested in the boundaries of mathematics, and actually do think we've put, for almost any generation, the mathematics you learn is going to limit you, because it sort of says those are the kind of problems we can solve. And I've written various articles about things you might want to call it soft mathematics, and I've done some collaborations with ethnographers and sociologists and people in ethnomethodology and design people about how you can sort of take mathematical approaches to design problems. And I worked for about 8 years on a post 9/11 CIA-funded project on, can we work out some kind of a framework that will help improve intelligence analysis, based loosely on mathematics and logic, but very loosely. So you're sort of in other words, looking at it fresh. No, because that's a great idea, but in the Defence Department, they wanted an answer in 6 years, which was not the way to do it. And so I just spent the money they gave me and didn't come up with anything. So that's that. In terms of the probability, we had a good time. I think I gave them money's worth in terms of time, but it wasn't the magic bullet that they thought they might want to get. In terms of probability theory, are we missing? So I think we can drill down on that one. And just to go back to that example about DNA profiling, there's 2 camps. There's the frequentists and the Bayesians, and usually the answers are at least very close, or they agree. When you apply it to cold hit DNA identification, if you do the calculation the way the Bayesians approach, the bigger the database gets of DNA profiles that the FBI stores, the more reliable a DNA match gets. And if you know how Bayes' theorem works, that's sort of what you expect. The frequentist argument says the more profiles you have in a database, the more likely you are, when you do a search for a cold hit, of finding an accidental match. You know, that's the argument that says the odds of winning the California lottery is 30 million to 1. How come people win? Well, because 30 million people or more buy a ticket. And it sort of wipes away the odds in a rather subtle way, but it wipes them away. But what is it, guys? Because the FBI is increasing the size of the profile database. It's about 3.5 million at the moment. As that database gets bigger, is DNA cold hit identification getting more reliable or less? You pick your probability theory approach and you get different answers. And these are all settling before the appeals courts right now, because in US law, if the relevant scientific community has not agreed on how to solve a problem, you can't admit it as evidence. So what's at stake here is the admission of DNA identification. This is big time stuff. It's going to end. Some of these are going to end up at the Supreme Court, and it's not clear how they're going to get resolved. I actually got into this because I was approached by several courts saying, we've got all of this expert testimony, we can't understand it. You've got a reputation for being able to take complex mathematics and make it intelligible. Will you tell us what this says? And it was kind of interesting, because I read the Bayesian stuff and it looks pretty convincing. And instinctively, I guess I'm a frequentist. And then I read the frequentist arguments, which has the backing of the National Academy of Sciences, as it happens, and originally had the backing of the FBI. And I read it and said, yeah. So I'm in agreement with two arguments which give diametrically opposite conclusions. So that, I think, shows, yeah, we are missing something in probability. We've got, and it's not just me, the experts in the fields are disagreeing. And when experts disagree on something so fundamental, we're missing something. Our understanding of probability theory is just not there yet. We don't have it, at least for that kind of problem. Yeah. Okay, Bob.
Yeah. Getting back to the Pascal-Fermat correspondence, all I know about it is what you've told us in the last hour, but I'm conjecturing that the real problem is, as you were hinting at, accepting the application of possible but not actual outcomes to something in the actual world. And we actually, we see echoes of this even today. Maybe we could work out an explanation of the argument between the frequentists and the Bayesians that you just cited in terms of this. But you see it in things like the Monty Hall problem.
Yeah.
The Monty Hall problem can incite an argument among mathematically educated people at the drop of a hat. And it has to do... That was never 5 minutes. Just and I think that this idea that counting possible outcomes is an acceptable way of drawing conclusions about the actual outcome. It may well be at the heart of it.
Yeah.
So it may be that Fermat could have more easily convinced Pascal by the argument, well, there's 3 chances out of 4 that player 1 should get all the money, and 1 chance out of 4 that player 2 should get all the money. But the idea of splitting the money according to the expectation, that doesn't follow from the arithmetic.
Yeah, it's sophisticated. I mean, it's a way of thinking about the world. But it did come very quickly. I mean, Ars Conjectandi was...
I was thinking this use of probability and statistics for actuarial tables may be a little easier to justify, because if you're an insurance company, you're not talking about different probabilities for a singular event. You're saying, well, I've got, I'm insuring 100,000 people, and my tables tell me that in the actual world, 80% of them will be dead by the time they're 85 years old. Yeah. But I think that people still, and again, going back to things like the Monty Hall problem, people have a very hard time dealing with the idea of attaching a probability to a single event.
Yeah. Yeah, well, it's a weird thing. I mean, you said, I'm going to toss the coin once. The probability of heads or tails, if you sort of ignore the physics, is 50%. But, I mean, to a single event, I mean, it's weird.
Or if you toss a coin and cover it, and you ask, what's the probability that it's heads?
So it's not in the future even,
Yeah, it's not even in the future.
Just,
Well, it's either heads or tails, so it must be probability one that it's heads or probability one that it's tails, but we don't know which.
Yeah, just surely this coin or something. Yeah. It's a weird phenomenon.
I think it's probably this problem Pascal had of understanding the application of the arithmetic, which he obviously could do, to the question of analyze a singular event. May be the source of his difficulty in having to accept.
And even today, if challenged, we say, what does it mean to say that single? So what do you say? Well, if you did it 100 times, roughly. I mean, so we immediately back off, and then so the obvious thing would be, well, have you ever done it 100 times? The answer is no. But I've just reasoned about it. So it's kind of weird that we don't even do it. We reason what would have happened if we did do it, and we feel comfortable doing that. And it works, right? I mean, if probability theory didn't work. But yeah, the Monty Hall, the two envelopes paradox, but those are two classic ones that show that we really have trouble coming to terms with this kind of reasoning. It's not a natural kind of reasoning. Not only is it reason, it's not natural. So we have huge difficulties grasping that kind of thing. And to say nothing of modern Bayesian approaches, where you do all sorts of weird stuff. And
So this is a question of kind of applying the same kind of history inductively. So we are, of course, standing on the shoulders of giants like Fermat and Pascal. So which were sort of the immediate giants that they stood on? So I know that Fibonacci did a lot of work in talking about the number system and how he did interest and all. So would you consider him one of those giants?
Quite a few of them I mentioned. I mean, Cardano had done a lot of the work, and it goes back to the 10th century. Galileo had done some work. Pacioli did some work. So the names I mentioned, whether you call them giants is a relative term, but all of the... First of all, it wasn't a difficult argument arithmetically. I mean, it's a simple counting argument. And people had been counting probabilities for some time. So everything was in place. It's not surprising that things happened so fast in terms of the mechanics, because there was nothing new to do. It was just the recognition that you could play those tricks that you'd been playing, do those calculations on this weird possible futures world. That's the only thing that changes, is the nature of the objects you're doing the modelling with. So it's not a surprise that it happened quickly in that sense. It was just that conceptual step. So what the import of the letter is, it creates the acceptance that you can do these reasonings in this futures worlds. Yeah.
What were the 17th century notions of fate?
Sorry?
So in the 17th century, did they still believe very strongly in fate? And was that part of the problem, that they had people that believed in chance at all?
They couldn't believe in chance at all.
Well, so, they talked very strongly about, or they believed very strongly in fate and the fates.
Yeah, one other interpretation, it maybe gets into the mix. During his life, Pascal had, I think I mentioned, several periods when he was intensely religious, and sometimes gave up mathematics because it was meant to be a pursuit of the devil, and you had to just contemplate heaven and the Lord and so forth. So he had periods of intense religious activity, and he's known for sort of writing about these things in pensees and so forth. So there's, and when he lost relatives and that kind of thing. So he's got this, he's known to have these things. So it could be that part of his problem, and it may be many other people at the time, were this sense that, the future is in the hands of the deity. And almost, you get it today when people object to people thinking about the Big Bang. That's taking science into a realm where it shouldn't go. So it may be that Pascal, somewhere in his back of his mind, had this fear that he was taking mathematics into a realm where humans shouldn't go, because that's God's realm and only God knows the future, and you shouldn't be there. There may be some sort of moral thing. I don't know. You can put that interpretation on it. and it's not an unreasonable thing to do, but I have no idea, and I don't know if there's any way of knowing that. It could well be that even if it didn't happen with him, it could be that other people had this same feeling that the future is not known. There's a couple of quotes I give, one of which is quite a bit later, by de Moivre, in fact, where considerably later, de Moivre, even in the face of all of this, has a statement that says something like, we can do all of this stuff, but the only person who really knows the future is God, and we just can't get there. So that certainly persisted a good century later to people who knew what they were doing in that area.
He mentioned that he said he couldn't put numbers in the future.
Oh, Aristotle said there are three kind of events. There are the sort of the necessary events, things which have to be. I guess you would say 1 + 1 is 2 is probably one of those. Let's pick a nice safe one. So there were the necessary things. Then there were the things which are sort of reliable predictions about the future, like the sun will rise tomorrow. I mean, maybe that's a necessary one, however you think. But let's pick one that's probably better. That sometime in the month of November in Seattle it's going to rain. Right? Okay. It's not a necessary truth, but boy, it's close. Right? So that would be, I forget the terminology used, but so you've got things which are necessarily true, things which are predictably true because the world keeps behaving that way. And the only other category is the unknowing. It's the category of things that are literally unknowable. The only person that knows is a god or a deity. Human beings simply have no access to that. Which in a sense is true. You don't know what's going to happen in the future, because what we got around that, as we sometimes do in mathematics, by getting at the future in a different way, by hanging numbers on it. We don't predict the future, but we do put numbers on it. But that was, I forget which work it was in Aristotle, but he talks about these, and I do mention this early on in the book, these three kinds of events: necessaries, predictable, and then the only other category being things about which we have no knowledge at all. They're just, the gods on Mount Olympus will roll their dice and we'll just have to take what will be.
Let me also make two comments. One, probably at the time, the view on the future was much more deterministic. The future is determined and God knows it. And second, about probabilities, I think it reached a huge debate was in 1910s, for Mises and so on, what probabilities are. And debate was never settled philosophically. Kolmogorov came with an axiom, and technically, sort of you could compute. So the problem which arises now with DNA, it goes back to this debate which was never settled on what probabilities really are. So we only know how to compute with them.
I mean, mathematicians have the nice get-up. We just write down the axioms and we don't worry about what they are. Right. It's still weird stuff. I mean, there's all this research by Kahneman and Tversky about people just make incredibly bad probabilistic predictions. Even statisticians do. You give them two identical scenarios and they will have a great preference for one over the other because of the way it's presented. Okay, thank you.
Thank you very much.
Well, I think this